Hello everyone, welcome to this video tutorial. In this video, I am going to solve this mechanical equation using the ANSYS Simplorer software. So in this video, we will learn how we can use these mechanical elements. Yes, here in physical domains, how the basic elements in the ANSYS Simplorer software, how we can solve that torque equation using these elements, and what is the logic behind mechanical modeling. So this is a video tutorial regarding this topic. Also, I solved this equation using the MATLAB Simulink software, just to be able to compare with the results that we get from the ANSYS Simplorer, right? To understand the simulation logic clearly. So, here in this equation, this is the electric torque. I am going to consider an electric motor. So this is the rotor, and as you know, we have this electric torque on shaft TE, and also we have this load torque TL. This is the moment of inertia of the rotor. This is the angular speed omega. This is the friction loss coefficient, and this term is the friction torque. Okay, so how we can solve this equation? In this example, I considered the electric torque equal to 5.2 Newton meter. These numbers are for a 1 HP electric motor, and the synchronous speed of this motor is 1500 RPMs. So the electric torque is 5.2, and the moment of inertia is 0.0017 kgm2, and we have the friction coefficient, and the load torque is a function of the rotor speed. As you know, we have this graph, the load torque as a function of speed. This can be a constant number, a linear function, or a quadratic function. So I am going to consider the load torque equal to KL omega 2, a quadratic load, yes, as a function of the speed squared. So in MATLAB Simulink, simply we can use these blocks to solve this equation. This is electric torque, and this is the friction torque. Here we have the angular speed, so we multiply it by the friction coefficient, the negative sign, and we can calculate friction torque. And this is the load torque. This is the angular speed to the power 2 times the coefficient KL is the load torque. And you know, here we can have this equation TE minus TL minus d omega divided by J. If we have this integration, we can calculate omega. So here, first I divide this summation by J, and I perform the integration to calculate the angular speed. And you know, if we multiply the angular speed by 30 divided by pi, we can calculate RPM, revolutions per minute. Yes, that is equal to omega times 30 divided by pi. So, if I solve this equation, here you can see the angular speed. The rated one is equal to 146, close to this number. And this is the rotor speed, that is equal to 1400 RPMs, close to this number. And this is the friction torque, is negative in opposite direction of the electric torque, is close to minus 0.1 Newton meter. This is the load torque, equal to minus 5.1 Newton meter. And finally, this is the electric torque, that is a constant. So, we implemented these blocks to solve this differential equation. What is the logic in ANSYS Simplorer software? So, let's add a Simplorer design and check these elements, basic elements, physical domains, mechanical. Here we have two different representations: displacement force representation or velocity force representation. What is the logic? How we solve an electric circuit? Yes, we have these two variables, voltage and current. Yes. So for each circuit element, we have a relationship between the voltage and current. And depending on different formulations that we have, we can solve the voltage of the circuit nodes or current of the elements. For mechanical representations, the force is corresponding to the current flow. And we can select velocity or displacement corresponding to voltage. Yes. So we have two different representations. So here, let me show you this. I pick this current source. This is a current source. You can see the direction of the current in this current source here. Its value is equal to 1 amps. The current enters into this element from this dot point. So now if I place the ground here and just I want to measure this current, so we need an ampere meter. If I place this here and place another ground here, yes. And here we have the simulation time. By default, I run the simulation, analyze. I want to measure the current here, the current of this current source. So report, rectangular plot, ampere meter 1 dot I, the current. As you can see here, the value of current is negative 1. What is the reason? Because the current enters to the element from the dot point. So here, this is in the reverse direction. And now, if I reverse the direction of this ampere meter, reference direction that we have, yes, the current enters from the dot point, and rerun the simulation. So here, the value of current is 1 amps. So we should care this dot point when we are going to use these elements to solve this equation. So yes, the mechanical force or mechanical torque corresponds to an electric current source. Okay, so here in physical domains, mechanical, if I use this representation, the displacement force representation, rotational, let's use this rotational torque source. Yes. So this is the torque source, and Control G to place a ground here. Also in measurements, mechanical, let's measure this torque. The value of the torque that we have here, and again a ground, mechanical ground, and run the simulation. So the value of torque is 1 Newton meter. If I plot the torque Fm root B1 dot torque, the value is 1 Newton meter. So now let's delete this part, and you can see the counterpart circuit, mechanical circuit that we have here. Now I want to generate this side. Actually, we have electric torque minus the mechanical torque minus the friction torque is equal to J d omega dt. So first we should construct this summation. So simply I can copy this, paste it here, and paste it here. This is the electric torque Te, that is equal to 5.2, and this is the load torque TL. Its value is a function of the speed, so I should use a pin to set the value of torque here, and this is the friction torque T friction. Also I am going to use pin. Yes, connect this to the ground and this to the ground, and here let's use this torque meter here, TE probe, show the TE probe, copy, paste, because later I am going to plot the torque waveforms for these three kind of torques that we have. This is T load probe. Yes, T load, and this is T friction probe. Yes. So now we add these three different torque types like KCL in an electric circuit, right? TE minus TL minus T friction. Then we should add this element, this rotational element. So here we have the mechanical ground, and here we attach this rotational mass. The moment of inertia is 0.0017. The initial angle is 0 and initial angular velocity is 0. So now I should consider a speed prop. Here we have rotational angular velocity meter. Okay. So like a voltage prop. Yes. This is like a voltage prop. This is like a current prop. So I place this here and I need to have the omega. Yes. To calculate the friction torque and electric torque. Let me flip this and flip this. Okay. And here I am going to construct this friction torque. We should multiply the angular speed with this friction coefficient. So copy this number. And here we need to add a gain. So where is the signal processing blocks? We have time functions, equations, and circuit here, blocks, math, signal processing blocks, continuous one. Yes, here is the gain block. Also, you can search here the gain to find the block faster. So yes, this is the omega times this number, friction coefficient. We can calculate friction torque. Yes, here is the friction coefficient multiplied by omega. That is in this case close to negative 0.1. So here, this is the friction torque. Okay. And for calculation of the load torque, here I consider this MATLAB function speed to the power 2 times this gain. So I copy this number and here I add this gain, but before that we need to add the function to calculate the speed. It's a square. So this is the gain. The load equation that we considered here, actually this is KL. And how we can calculate the power of the speed? Here we have this block, the power block, the exponent is 2. X to the power n, and this is the gain. Okay, so yes, this is the logic that we have for calculation of the speed of this rotating element. So let's set the simulation time equal to 0.5 second and run this simulation. So delete all previous results. Where is the angular speed of the mass prob1 dot omega? Yes, this is the angular speed. Here you can see the rated one, close to 146.4. Yes, the number that we have here. As you can see, we reached the steady state speed after 0.15 second, 150 milliseconds. Okay, 150 milliseconds. We can get the same curve here. So you can compare this Simulink model, how we solved that torque equation here, and how we solved the torque equation here. Yes, calculated the friction torque, the load torque, this circuit, and this math element. Also, you can plot the value of the friction torque. Where is the friction prop? Is here. And also the load torque. Yes, the load torque is close to negative of 5.1 and friction torque is close to negative 0.1. This is millinewton meter. Negative 100 millinewton meter, that is negative 0.1 newton meter. So yes, you can redo this example in the ANSYS Simplorer software and generate the results and analyze. So the aim of this video was to explain the logic for the mechanical circuits, how we can use the torque source element, the torque meter element, the speed meter element, and the rotational mass element to solve this torque equation. So let's continue in the next video. Thanks for watching.